let's start with the simplest sequence. What could be the simplest sequence that you can think of? AK. 0, right? It's all zeros. And then what is the sum? Sum is always 0, right? Next meaningful thing is maybe 1. Just don't introduce k, and then it's going to be very simple, right? AK. So what is Sn? Let me use n, so you understand this. You get used to the switch of a parameter, the variable there. K going from, well, this time 0 is alright. Is alright? It could be 1. This because it defined everywhere. It is up to you how you define it. If I go from 0, let me just go to n. Is it numbers easy? Go up to n, and we're adding this AK in there, right? What is AK? Always 1, right? Always 1. So this one, it seems like we're just adding 1 and 1. How many times? Every time that is coming from this index counter, right? So that's n times, right? Adding 1 n times. So what is it? N. All right. So that's what we're looking at. If you're looking at 1, your answer is, n. It's like, what is the antiderivative of 1? You say it's x, right? Doesn't that look just like that? But that's not the answer for the rest of the thing we do. So you shouldn't do it that way. All right. You realize that if you enter quickly, that what if next to simpler thing would be my an being just n in there, right? What could that be? Then you write down Sn, k going from 1 through n, ak. And what is ak? AK is k. If an is n, ak is going to be k, right? So there's a k. All right? So let's see. This one means that first number is 1, and second number is 2, and third number is 3. Go all the, what is the last number? N. Right? Just computing that. It doesn't seem as easy to come up with a formula that matches this one. So it requires a clever idea. Somebody figure that out and all that. But we're expecting what? This answer could be written in terms of the things we understand: sine, cosine, exponential, logarithmic, polynomials, n factorial. That's what we want, right? So doing it backward, it seems like more productive than attacking this problem. It's a lot harder. So let me make this analogy with you. If I put it like this, dt, that requires a lot of work, right? And we didn't even start this antiderivative problem like this. We started with a lot easier one, such as this one. I don't know what that goes in there, but I want to make that answer to be exactly like ln t plus 1. That's a lot easier. Just examine that you can solve the problem that you can easily solve first, right? So that was the basic table of integral. That's how we started. Remember? When we start integral problems, there's the basic things we don't ask because we see it. In our memories of our practice of a derivative practice, you see it. So I don't ask the integral of sine x is negative cosine x. Right? You accept that. Nobody proved that, right? So it's like that. What integral becomes ln t plus 1? Anybody remember this? Integral of ln t plus 1 is hard, but this question is easy, right? This one going in there, what operation should we do to fill in this antiderivative part? Is a derivative, right? Correct? Yeah, it's a derivative 1 over t plus 1. So your table is actually, integral table is like this. You actually put in an easy answer and see what should go inside the integral. That's why we shouldn't ask questions, right? So we're going to do the same thing. I don't know what this one ak will be, but I want Sn to be a simple function like n. Sn to be a simple function like n squared. Something that we expect a simple answer and figure out ak backwards. Okay, answer here and figure out integrand function backwards. So here's the basic facts that we're attacking. If you want this thing to be answered, start with something that we can handle, which is doing it backward like this. All right. This is a basic fact, and an idea is that the process going from here to there is derivative process, right? What is a derivative? The rate of change of values, right? Values changing. So you take this one and the minus the slightly different value and things like that. That gives you an idea. Idea is the following: Sn minus Sn minus 1, and see what that is. This one goes to 1 through n of ak plus k going 1 through n minus 1 and ak. By definition, Sn is the sum up to n. By definition, Sn minus 1 here is sum up to n minus 1, right? And I was wrong. This is supposed to be negative in there. So can somebody do this one in your head? If you have all the terms from a1 through an, let's not just talk. The one problem I have is just talking and not writing things down. Sometimes I should do that. The second one is all the way up to n minus 1. And if I just specify last two terms, get clearer, n minus 1, and then you finally arrive an. That's the first sum, and that's the second sum. We're subtracting off each other, right? So do you see a lot of overlap in there? 1 through an minus 1 is there, and 1 through an minus 1 is there. Exactly the same, right? So they all cancel, they're leaving what? An in there. Is that correct? So that is kind of analogous of a derivative that you're doing. If I have Sn over there, what could be that ak in there? It's a derivative in terms of, for the integral here, just take the difference, and then it'll tell you what an is, right? That whatever the easy formula you have, that an must be this one, then you have a nice formula. So that is the basic idea. So I want you to write it like this to clear. This is a formula we're going to use. Sn and Sn minus 1, analogous to derivative, is going to be an. That's what we're looking for. And also you have to be careful that this formula is valid only for whatever that your index starts with. So what is the lowest s value considered? If it is a 0, then you can't put more than 1 in there. So in this case, maybe n should be greater than or equal to 1. It depends on what is the lowest index it is defined. So this is the formula that we're going to use. Entire partial sum up to n minus partial sum up to n minus 1. Of course, you have the very last term, which is an. Right? And make sure you always tag this so that you get the correct answer correctly. All right. So we approach the problem an opposite way, that if we have an, and what is this Sn is a formula, it's backward. That seems like a harder problem. So why don't we start with Sn being n in there? What could be ak? That's what I'm talking about. Right? Backward problem. Right? You probably know the answer already. What was the answer for Sn being n? We just calculated up there with an being 1 in there. We got this one, right? Is that correct? So when an equals 1, Sn became n. So doing the backward problem, if Sn is n, what is ak? It's probably 1. Number 1 in there. Correct? So we're going to discover that by using this idea, and then push that to the next level, and then it's going to surprise us. So let's do that. All right. If Sn is n, what could be that ak? You don't know, but here is the formula. If you can calculate the left-hand side, that tells you what this one is. Right? So here, the idea, I don't know that. But Sn minus 1. This formula, by the way, makes sense. Let's say n greater than or equal to 0. So what is Sn minus n minus 1? Sn is n. Sn minus 1 is n minus 1 in there. Is that right? Because Sn is n. If the subscript is n minus 1, Sn minus 1 is going to be n minus 1. Correct? So that's the exact formula, n minus 1. So what is it? It's 1. Correct? So this 1 is going to be ak. So we conclude that ak is 1 for what kind of k values? This formula only works for the lowest index that is allowed in here. So let me change to n. Sorry about this. Since we're in terms of n, we should be in n. That an should be that. And this is only valid for n greater than or equal to 1. Is that right? So we almost got everything except a0. This formula only allows you to everything except the very first term. So you enter like this. All right. In general, Sn is going to be, because n is considered to be 0, we start from 0 to n and ak. Right? That is the definition of Sn, and we know what this one is n. We have a formula ak that is greater than or equal to when the index is greater than or equal to 1. So we don't know what a0 is, but you have to set aside a0 there. And just focus on this part, k equals 1 to n and ak. That is supposed to be n, but we know the formula ak for index greater than or equal to 1. So we can replace that ak with the formula we discovered, right? So here's a0 and plus k going from 1 through n. And the formula ak is always 1, like that. All right? So what is the first term? That first term can be calculated. First term is this, S0, because index starts from 0. S0 is the first term always. So that is because of the formula is a 0, and that should be the S0. So that's really 0. So you can see it doesn't really come into play here. So what we have discovered in here by looking at this idea, n is equal to k going from 1 through n of 1. That makes perfect sense. You add 1 n times, then you get n back. We discovered this in a slightly different way, right? Does that make sense? Right. We're going to do the next one together, and that's going to be more fun than this one. All right. Just like integral techniques, this is also a lot of work to doing carefully. And here's our summary again. Sn minus Sn minus 1. What is that supposed to be? Remember this formula all the way up to nth term, minus all the way up to n minus some last term, right? What is the last term in there? Is it an? And this one could be one formulation. This n greater than something can vary to 0 and 1, usually like that. So that's the idea. And we started with Sn equals 1, Sn equals n. We realized an interesting fact that from there we discovered the formula k going from 1 through n of adding up 1 is n, which is, it has a lot easier proof than what we just did. So let's go to the next level. What is next level n you want to try? N squared, right? That is kind of the simplest function that you learn before you enter difficult functions, sine and cosine and things like that. N squared. Is that right? Okay. So we're going to do this and figure out the formula s equals. This one still makes sense, n greater than or equal to 0. Is that okay? This formula seems like makes sense. N greater than or equal to 0. So we'll keep it that way. And it's going to be a silly exercise, but need to have a little break out of this. Just keep listening. So I'm going to we could do that. You can calculate this part, and I'll do the rest of the part. So exercise today, probably the only exercise in terms of time, is the following. So compute an and simplify. It's very simple algebra, right? That's all I have to do. And I will take it from there and to what we can discover from there. Right, was the exercise simple enough? Right? Alright, so the conclusion is this. If you simplify that Sn and minus Sn minus 1 is n squared minus n minus 1 squared, the answer is 2n minus 1. So that part's simple. And this part you have to be careful. You have to always aware that this formula you just calculated is only valid for n greater than or equal to 1, right? It is missing the first term a0. What is a0? It's always equal to s0. If your partial sum starts from n equals 1, that one is the exceptional part. So a1 is s1, right? The very first term in the partial sum is always the same as the first term in the partial sum is the same as the first term in the sequence. Does that make sense? So according to the formula Sn squared, what is this S0? The 0 in there, right? So when you calculate An, don't just leave it here and you complete the the remaining part is not covered from the formula. You just list them down. Is that okay? The next thing we did, that's the end of the solution there. Next thing we did is entering this Sn in there. We have a formula that is n squared. By definition, this one goes like this: k starting from 0 to n and a k. And we wanted to figure out what that a k is, and we figured it out. This seems like a story, but if you put that formula in there and rearrange it, you get a better formula, and that's why we're doing this one. All right? So what was the formula of ak? 2k minus 1. We figured that out, right? But we're not going to stick in 2k minus 1 in here. You know why? That one is only valid for k greater than or equal to 1, correct? So what should we do with a0? You have to set that aside because the formula does not apply to a0. And only look at the summation shortened like this so that we can replace all the ak with the formula we have discovered. And here, what is a0 then? a0 we discovered is a 0, so it doesn't really affect in here. If you plug in n equals 0, it picks up -1, right? So we can't extend this formula to n equals 0, and that's why we're treating like this. All right? So what else? And that's a 0, and then we plug in what? ak, the formula of this one, right? It's a 2k minus 1 in there. That's what that is. Okay? And this whole thing is supposed to be equal to what? N squared. We started from n squared. We want to figure out what should be the sequence that whose partial sum is n squared. And we analyze a little bit and try to simplify it inside of this one like that so that we can remember this formula. So from here is the manipulation. We got k going from 1 through n. 2k minus 1 is n squared. Seems like you can isolate the k in there. So you see there's a sum of two things in there. So you can split the summation, just like integral. It's logical in there, right? So inside is a sum of two things. You can look at it as a plus -1. Then you can split that, distribute that summation symbol like integral to the individual term. Is that okay? Any question about this one? Good. So how about this -1? Isn't that constant? You can pull that out. Isn't that 2 constant? So that we can pull that out. That's nice. And here you can see this is a problem we wanted to solve before. Remember? Inside is a k. It's going to be 1 plus 2 plus 3 plus up to n. What is that? You can isolate this one using this thing. So it's minus. If you pull out -1, what's inside here? Invisible 1 is a multiplicative. We factored out. There's a 1 here. And n squared. Correct? So we don't know this. It seems like we want to solve this equation for that part right there. So here's a 2. K in there. Who remembers what this one is? Summing up n times, always the same thing, 1, 1, 1. What is the answer? Was n, correct? Adding 1 n times is n. What about the right-hand side is n squared? So make sure that we understand the summation stops right there and n is a separate term out there. All right? So try to look at it this way. It's a lot like really the integral operation in terms of this last bit of algebra in there. So we want to isolate this sum 1 through k in there. So it's 2 k1 through n of summing up the simple number k is now equal to n squared plus n. Is that right? And you divide both sides by 2 and finally arrive formula k going from 1 through n, k equal to n squared plus n divided by 2. All right? So we arrived at an interesting formula. This one says if you add 1 plus 2 plus 3 all the way up to n, usually you have to do this process of n operation. It's actually a lot simpler. You can just do 3 or 4 operations to calculate that. Right? So this is again analogous to if you know the antiderivative, what should be the integrand function inside, and you can easily calculate that. From there we create a table of a basic integral table, right? So do the same thing, put the function that we can handle to the partial sum, and we can create it inside and create a nice formula like this. So what is the next thing we should try? Sn equals n cubed, right? And if you try that, and it's going to give you another interesting formula, and so on. And this will also give you another interesting formula. What is the next general? If you're looking at this polynomial n squared and n cubed, what is the next entrance? Probably reciprocal of that. That's 1 over n squared. And if you do that, it is not as interesting as this one. So we're not going to enter that. But eventually you will have that. They have this one in the end of this section. So next reasonable thing is exponential and log. And next reasonable thing is a trigonometric, right? Put that Sn, trigonometric function, see what kind of thing you get. And trigonometric thing is a very limited algebraic simplification, so you don't get anything too interesting. So seems like next exponential thing is interesting, which is Rn raised to n. That's the exponential, right? R fixed, exponent, n varies. If it is like that, what kind of AK do we get? Right? Doing backward again. So that's one thing we're going to do today. Remember, these are not infinite series. You know, truncated the finite term. And you need to understand this part clearly before you enter the infinite sum. That's why I'm spending time on this one. All right, so let's do this one. Sn Rn. That's our question to that. And the answer to this one is not going to be like this. That's going to be just swung by and not really paying attention to anymore. This is very, very important result throughout the rest of the semester. So what is this? The question. Okay? So we're going to do the same thing we did of all that and pull out some interesting formula. So let's do this. How do we start this? Sn minus Sn minus 1. So all this thing makes sense with n greater than or equal to 0, right? So that's how we're going to start. This time, the a0 is not 0, right? What is r to the 0? If r is non-zero, it's 1, right? So your first time is 1. So that is supposed to be an, and for n greater than or equal to 1. So we're missing information about a0. So what is Sn? R to the n, right? What is Sn minus 1? R to the n minus 1. Is that okay? And that's your an. As simple as that. These two terms, still algebraic, nice, so you can simplify a little bit further. So that this is what they do. R to the n minus 1, R minus 1. Is that okay? That's the lowest power. You factor it out. And think about 3 and 2. Factor out 2, you're left with 1 power in there. And that's what your an is. Okay? For n greater than or equal. How about a0? Remember a0? a0 was 1, which was s0. Very good. We got the formula. Good thing is that this one is a constant, right? Just like a 2n minus 1. Remember 2n minus 1? Your answer for problem number 5 in the test. Part B, 2n minus 1. So we isolate it to we're not interested in 2n minus 1. What is the sum of this, And if I put the sigma here, sum in summation, what is that thing? So we enter the answer to the right there. That was a part C, right? So here's a constant. Here's the n part is actually varying. Why don't we just isolate that part? And it seems like that's going to give us a nice result. So here, Sn, which is supposed to be r to the n, right, is equal to summation k going from 0 all the way up to n. Is that right? Yes. And which is equal to what? AK, right? That is a partial sum. And what is the next thing we usually do? R to the n. And you set aside A0, right? Because according to that formula, when n equals 0, does that hold? N equals 0 is 1 over r and r. So when n equals 0, that formula gives us this type of a thing, right? Which is not necessarily 1, is it? That's why we need this information right there. Does that make sense? Okay. If you plug in a equals 0, just to see if this one still holds for that fact that we stated there, and it's not. So you have to separate it like this. A0, and how's the index starts here? From 1 to n, and AK is here. Now this AK has nice formula. Then you switch to that formula. Rn. What is A0? A0 is just 1. And here k going from 1 through n. What is this AK? AK follows this formula now. Is that right? So that's r to the k minus 1 and r times minus 1, right? Here, if r is not 1 and this is non-zero constant, and you can divide it, right? If r is 1, it's probably very simple. R is 1, 1 to the n is all 1. So from the beginning, we kind of know the complete answer to that problem when r equals 1. All right, so let's enter this one. Remember, think about all the manipulation you do with the integral, changing variable and split and pull out a constant. It all holds. Remember, these are all Riemann sums. The integral is defined in that way. So what are you going to do? I guess we're interested in this chunk right here that actually has k in it. So I'm going to factor that out. How do they do this? I think they do this like this, r to the n minus 1. And r minus 1 is factored out because there's no k, the summation variable, in it. Just like there's no dt in it, t in it, you can pull out of the integral. That's interesting, right? That's something that going to be good information. So now you're dividing. If r is not 0, not equal to 1, and then you can divide it. R to the n minus 1 divided by r minus 1 equals k going from 1 through n, r to the k minus 1. Right? That looks like a nice, very nice, simple sum and formula, and then there is a nice closed formula there. Right? So we can look into it. So what is an? The answer stops right there, right? And this is a little bonus that comes out of this consideration. We're doing this because of this bonus part that is coming in there. Again, this problem itself ends right there. And we further isolate it to get a nice interesting formula right there. All right. So left-hand side is good. Just to understand what this one is, I'm going to list those first terms. So who knows what the first term of the summation is? K goes into 1, and r not being equal to 1. What is the first term in this summation? K going to 1. So r to the 1 minus 1, right? R to the 0 is 1, correct? What is the next term? R to the 2 minus 1, right? So it's r to the first. And 3 minus 1 r to the second. What is the last term? The last term is n. N is going in there is r to the n minus 1. All right? Is that okay? So if you're looking at the sum, then all this thing is simply r to the n minus 1 divided by r minus 1. Okay, that's a nice formula if you sum up this exponential form. And they describe the relationship like this to go from, this is a sequence, right? So what kind of sequence is this to whose sum is being like this? This is the first term what operation do we do to go to the next one? You multiply by r. Is that right? And to go to the next part, you do the same thing, multiply by r. And to go next one, you multiply by r. So the sequence that is involved in here, not AK, but a simplified form, is a sequence you get to the next part, you just keep multiplying in there. So r to the k minus 1. This sequence is called geometric sequence, and the sum here is called geometric sum. And if you take that into infinity, it's called geometric series. All right? So it's geometric sequence is what it is. However, they tend to re-index this thing. You see this a minus b and c minus d, you can swap the order, so they have tendency to write backwards like this, and you will see why later. I have a formula. And for that part, we're going to do substitution, right? Substitution rule. How the substitution rule goes in the integral. In this summation, substitution rule is very limited. You can't just do freely as you did in the integral. It has to be just a shift. So rather than writing k minus 1 like this, I'd like to write it just simply just a j in there. It's a lot easier to write it that way. Is that okay? There's no derivative, multiply, reciprocal. It's just a simple shift. So the whole summation is rewritten from j going from something to something and r to the j. Is that right? Because whole k minus 1 is represented by new variable j. So here, k varies from 1 to n. When k is 1, what is the j value here? When k is 1, j is 0, right? Correct? How about when k is n minus 1, and j is n minus 1? So when k is varying from 1 through n, j is varying from 1 through n minus 1. Okay? So very first term now we re-index to j0. Last term is re-indexed to j n minus 1. Correct? Once you enter like this j thing is not important. Just like integral dt can change to dx as long as there's no j's out, k's out there and confusing, right? So you can re-index, go back to k again, like this. So they prefer this one, something started from index 0, if possible, to go whatever the last term is. All right? So that's the fact that you have to remember. This is a geometric sum. So let me summarize it in this way. Geometric sum. This way here, we discover this by looking at obvious example of Sn r to the k. If you're looking at the sequence whose common ratios of adjacent terms all common, right? Then that's r here, and formula is 1 minus r to the n minus 1 minus r. Okay? If everything is perfectly organized like this, of course you're going to recognize r, you're going to recognize n easily. But sometimes this formula is all indexed differently, and r, the inside is not simple as r to the k, is all complicated looking, and the following usually is a good idea to recognize what is involved in what in here. This is, if you look at it, this is AK. That's different from our earlier AK, okay? But if you just look at this problem independently, and that's our AK, formula looks simple, complicated, then how do you recognize the common ratio? You want to enter here something like this, and you want to enter this formula. That's the purpose usually. Then you take that two formula and take the ratio. And what is that supposed to be? Remember how to go to next term? You multiply by r, right? So if you take the different quotient, it's supposed to be r. In fact, this is how you actually recognize whatever you're looking at here is actually geometric sequence. Let me repeat that again. You're looking at some complicated formula. It doesn't look like simply r to the k. How do we recognize it's a geometric sequence? AK plus 1, the formula divided by AK, simplified. If that is independent of k, you know that's a geometric sequence, right? It's actually a pretty good idea to recognize it and do calculation really quickly. So I know R, here's a massive expression, that's how you figure out R right there, right? Well, next thing you have to figure out is N. Okay, that's what R is if it's messy. How do you figure out N quickly? Is that number of terms, not the end number or anything like that. Here's how many number of terms in there. End index, right, minus the beginning index is not really the number of terms. If you go 0, 1, 2, 0, 1, 2 has 3 terms, right? But 2 minus 0 is not telling you the right number of terms. So you always have to one more, because as you subtract, you ignore the very first terms counted. So last term, index minus the first index plus 1, right? That always tells you right number of terms in there. So what is it? N. That's what it is. So to use the geometric sum formula, you take the quotient of adjacent terms, recognize that this is the independent of k, and count the number of terms in that sum, and then it's just simply 1 minus r, r to the n, 1 minus r. Okay? So that's the fundamental formula. So a little bit more general formula is that, what is the first term of this one? What is the first term? R to the 0, right? Which is 1. So this sequence starts from 1 and multiply r and multiply r, things like that. But they realize that this 1 is not very important.